Hello everyone, this is Jesse Crawford with New York Medical College, and this is the supplemental lecture on the normal probability distribution. You'll recognize this first slide from the second lecture video. It shows a histogram for a sample of adults' heights and a normal probability distribution in red. Recall that the histogram is a bar graph that tells you how many people have each value of your variable. So for example, this histogram shows that there are 14 people with a height of 64 inches in this sample. And this histogram is relatively well approximated by the normal probability distribution. And there are a lot of variables in nature that are well approximated by a normal probability distribution. And so for this reason, we're interested in studying normal probability distributions. Variables like height, weight, exam scores, and a variety of other variables are approximately normally distributed. This slide shows a normal distribution, which is a pretty good approximation for Math SAT scores. The first thing that we want to say about normal distributions is they have two important parameters, the mean and the standard deviation. Now, if you looked at all students who took the Math SAT, the average score would be about 500, and the standard deviation is about 100. And you can actually see those numbers in the graph. The mean is the center point of the bell curve, so that's 500 in this example. And the standard deviation is the distance between the mean and a certain point on the graph. If you look at the graph, you'll notice there's an inflection point where it changes from being concave down to concave up. And the standard deviation is just the distance between the center and that inflection point, which is 100 in this example because the standard deviation is 100. You don't really need to know about that inflection point. It's not a big deal. What you mainly just need to know is that the mean of a normal distribution is the center of the bell curve, and the standard deviation is going to be bigger if there is a lot of spread. If the bell curve is really wide and spread out, you'll have a high standard deviation, and if the bell curve is tight and narrow, then you'll have a small standard deviation. As mentioned before, this normal distribution is a pretty good model for Math SAT scores, and there's a random variable in play here. If we randomly selected a student who took the SAT and we looked at their Math SAT score, well, that would be a random variable because we're going to get a number if we do that, but the number that we get is randomly determined. And you know that we use capital letters to represent random variables in probability theory, so let's use capital X to represent the Math SAT score of a randomly selected student. Well, then capital X has a normal distribution, and the mean is mu, and the standard deviation is sigma. And you can see that that's the notation given here. We have capital X and we have a tilde. That tilde just means has the distribution of. And then on the right it says a normal distribution with mean mu, and it actually has a sigma squared there. And keep in mind that sigma squared is the variance. So probability theorists prefer to use sigma squared, and they prefer to use the variance instead of the standard deviation a lot of times. So that's why the notation is like that. But basically, if you read that equation, it says X has a normal distribution with mean mu and variance sigma squared, which is equivalent to saying the standard deviation is sigma. And then you can see if you go further that that's a normal distribution with mean 500 in this example and standard deviation 100. In order to find probabilities using a normal distribution, it basically just boils down to finding the area under the curve in certain ranges. And it's not a bad idea to know some of the more commonly used areas. Now, the first thing we can say is that the total area under a normal curve is equal to 1, or 100%, however you want to look at it. And that corresponds to the fact that the total probability is always 1. This slide shows that 68% of the area is within one standard deviation of the mean. So in this example, our mean was 500 and our standard deviation is 100. So if we go to the left by one standard deviation, we're going to do 500 minus 100 is 400. If we go to the right by one standard deviation, we're going to do 500 plus 100 is 600. So this means that 68% of the area is between 400 and 600. But keep in mind, the total area under the curve is 1. So if 68% of the area is in that range, then that means the area in that range is equal to 0.68. Another way to look at this is 68% of the Math SAT scores are between 400 and 600. And even another way to look at it is that if I randomly selected a student who took the SAT, there's a 68% chance that that student's math SAT score would be between 400 and 600. And that's shown in the fourth bullet with that equation. The probability that 400 is less than or equal to x is less than or equal to 600 is equal to 0.68. This slide shows a similar principle, but it involves 2 standard deviations instead of 1 standard deviation. 95% of the area is within 2 standard deviations of the mean. So in this example, since the standard deviation is 100, 2 standard deviations is 200. If we subtract 200 from 500, we get 300. If we add 200 to 500, we get 700. So 95% of the area is between 300 and 700. That means 95% of the math SAT scores are between 300 and 700. And that means if we randomly select a student, the chance that their math SAT score is between 300 and 700 is 0.95. Finally, we have this slide which shows that 99.7% of the area under a normal curve is within 3 standard deviations of the mean. And that for our math SAT example, that means that 99.7% of the SAT scores are between 200 and 800. Now in reality, 100% of math SAT scores are between 200 and 800. The exam is just set up that way. The minimum score you can get is 200, the maximum score you can get is 800. So the normal curve is actually giving us a slightly incorrect probability here. And that's because the normal curve is a mathematical idealization. The population of math SAT scores is not truly normally distributed, but it's a very good approximation, and it's an approximation that has a lot of theoretical value for us. It's also worth pointing out that the normal distribution actually extends infinitely far in both directions. But since 99.7% of the area is within 3 standard deviations of the mean, in most practical situations, you can basically assume that the entire population is within 3 standard deviations of the mean. Now we would like to move on and start actually calculating some probabilities with the normal distribution. But before we can do that, we actually need to look at a special normal distribution, which is called the standard normal distribution. A standard normal distribution is just a normal distribution with mean 0 and standard deviation 1. So we can write mu is 0 and sigma is 1. And the notation that we use for a standard normal random variable is capital Z. So you'll notice there that it says capital Z has a normal distribution with mean 0 and standard deviation 1. Now let's look at how those 3 special rules we just learned apply to a standard normal distribution. Now the first of those rules said that for any normal curve, 68% of the area is within 1 standard deviation of the mean. But for a standard normal distribution, the mean is 0 and the standard deviation is 1, and so that means the area between -1 and 1 is going to be 0.68. Similarly, the area between -2 and 2 would be 0.95, and the area between -3 and 3 would be 0.997. I just want to emphasize that these facts are not true for any normal distribution. They're only true for a standard normal distribution, which means that the mean is 0 and the standard deviation is 1. And again, these random variables are so special that we use a completely different notation for them. We use the notation capital Z for a standard normal random variable. So these 3 equations on the slide are basically just stating those 3 rules using mathematical notation. Okay, so since a standard normal random variable is between -3 and 3 99.7% of the time, when we're drawing the standard normal curve, we usually just draw it from -3 to 3, and we don't worry about the values outside of that range. And if you get a value of Z that's bigger than 3, like 6, there's actually a decent chance that you made an error, and it might be worth your time to go back and check your work to make sure you haven't made an error somewhere. On the other hand, you really can get values of Z that are quite big, like 6, and we'll actually see in some of the later chapters that this has some important statistical consequences when it happens. Now you might be wondering, why do we care so much about standard normal distributions? And the answer is because we can actually calculate probabilities for standard normal distributions using the normal table that's in Appendix B of your book. Now look at the picture here. It shows a normal curve, and then it has a number Z at the bottom of the curve. And you'll see that all of the area to the left of that point is highlighted. What this means is that if you have a particular number that you're interested in and you want to find the area to the left of that number, all you have to do is look that up in this table. So for example, if you wanted to look up the number 1.47 in the table, then you would get 0.9292. And that means the probability that a standard normal random variable is less than or equal to 1.47 is equal to 0.9292. Alright, this slide just shows how to deal with a question that we discussed on the last slide. The problem says, how much area under a standard normal curve is to the left of 1.47? Then it also says, find the probability that z is less than or equal to 1.47. Now, it's important to keep in mind that these are really the same questions. When you're dealing with a normal probability distribution, the probability that the random variable is in a certain range is just equal to the area under the curve in that certain range. So if you want to find the probability that the standard normal random variable z is less than or equal to 1.47, that's the same thing as finding the area under the curve that's to the left of 1.47. So to find this probability, we just need to look up the number 1.47 in the table. We just find 1.4 in the column on the left, and we find 0.07 in the row at the top. Then we just find where that row and column intersect, and we get 0.9292. So that means the area under the normal curve to the left of 1.47 is 0.9292. And again, that tells us the probability that z is less than or equal to 1.47. It's important to keep in mind that this table can only tell you the area that's to the left of a number. If you want to find the area to the right of a number, you're going to have to do something a little different, which we'll see in a second. And if you want to find the area between two numbers, you're going to have to do something else as well. So this table only gives you the areas that are to the left of numbers. This slide just shows another problem that's very similar to the last problem, except we're trying to find the area to the left of negative 2.35. If you go to Appendix B in your book, you'll actually see that you have two normal tables. One is for positive numbers, and one is for negative numbers. So just make sure that you're using the right table. If you want to look up a positive number, you'll use the table that was on the previous slide, and if you want to look up a negative number, you'll use the table that's on this slide. Also, you won't be able to use the tables that are on these slides for every problem because these tables on the slides are incomplete. So for some numbers, you will actually need to look up the tables in your book. So to finish up this problem, we're trying to find the area to the left of negative 2.35, and so we just look up negative 2.35 and we get 0.0094. Alright, let's consider an example where we're trying to find the area to the right of a number. So this problem says, how much area under a standard normal curve is to the right of 1.47, which is equivalent to finding the probability that z is greater than or equal to 1.47. Again, the table only allows us to find the area to the left of a number. So on this problem, we're going to have to do a little bit of manipulation to get the problem solved. So the picture here basically shows how to do the problem. The area that we want is the area to the right of 1.47, which is the first area shown in the picture. But that's the same thing as the entire area, which is equal to 1, minus the area to the left of 1.47, which is equal to 0.9292. So if we want to find the area to the right of 1.47, we're just going to do 1 minus 0.9292, and we'll get 0.0708, which is the answer. The equations below the picture just show this in mathematical notation. We're trying to find the probability that z is greater than or equal to 1.47. Well, that's just going to be 1 minus the probability that z is less than or equal to 1.47. And then we can use the table to look that up and get 0.9292, and to complete then we complete the calculation and we get 0.0708. What should we do if we want to find the area between two numbers? This problem says how much area under a standard normal curve is between negative 1.36 and 0.83, and that's equivalent to finding the probability that z is between negative 1.36 and 0.83. Well, the picture again just shows how to do this. We want the first area that's in the picture, which is between negative 1.36 and 0.83. Well, if we looked at all of the area to the left of 0.83, and we just get rid of the stuff that's to the left of negative 1.36, we'll be left with the area between negative 1.36 and 0.83. In other words, the area between negative 1.36 and 0.83 is equal to the area to the left of 0.83 minus the area to the left of negative 1.36. And so we just have to look those two areas up in the table and then do a subtraction. So we end up doing 0.7967 minus 0.0869. Those are the numbers we get in the table, and the result is 0.7098. Now, the equations below the diagram show you how you would think about this solution using mathematical notation instead of pictures. This problem says find the probability that z is equal to 1.47. Well, the answer to this question is 0, and the reason for this is the probability that z is equal to 1.47 is equal to the area under the curve at exactly the point 1.47. But that's just a line segment, and the area of a line segment is 0. There's nothing special about the number 1.47 here. The probability that capital Z is equal to any particular number is equal to 0. I know this seems a little weird because you might be wondering, well, how is it possible for Z to be equal to anything if the probability that it's equal to any particular number is 0? And that's a really good question. The best way to think about that is there are infinitely many possible values of Z. Since Z can be equal to decimal numbers, and it doesn't have to just be equal to whole numbers, it can be equal to anything. It's a continuous random variable. And so that means that if the probability that Z was equal to particular numbers was bigger than 0, then all of those probabilities would have to add up to infinity, because you would add those numbers all up and you would get infinity. So the probability that Z is equal to any particular number is 0, but the probability that Z is in a range is a positive number. So that's the best way I can explain it. That's the best way to think about it, I think. Now, what is the consequence of this? Since the probability that Z is equal to a specific number is 0, that means that you don't really have to worry about the distinction between a less than or equal to sign and a less than sign. For example, if you want to find the probability that Z is less than 1.47, that's the same thing as finding the probability that Z is less than or equal to 1.47, because the only difference is that in one of them Z can be equal to 1.47 and in the other one it can't. But since that has 0 probability, it doesn't affect it to remove it from the probability you're trying to calculate. And that pertains to any less than or equal to sign that's inside of the parentheses for any normal random variable. You can just disregard the difference between a less than sign and a less than or equal to sign. And this doesn't just work for normal random variables, it works for any continuous random variable. But it's important to remember that it does not work for discrete random variables. In particular, for the binomial distribution, this will not work. One example we looked at for the binomial distribution was if someone shot 10 free throws, how many of those baskets would they make? And there's going to be a big difference between the probability that someone makes at least 8 baskets and the probability that they make more than 8 baskets. The difference is resulting from the fact that there's actually a chance that they'll make exactly 8 baskets, and so if you ignore that, you'll be making a mistake. Okay, now that we've figured out how to calculate probabilities for standard normal random variables, we can actually calculate probabilities for any normal random variable. For example, let's look at this problem. It says SAT math scores are normally distributed with mean 500 and standard deviation 100. So this is just the distribution we were looking at the beginning of the lecture. Then it says, what percentage of students have SAT math scores between 350 and 620? Okay, to start off the solution to this problem, let's look at the mathematical notation that's below it. It says probability that x is between 350 and 620. That's what we're trying to find, right? Okay, now let's keep in mind one thing. We are not dealing with a standard normal random variable right now. A standard normal random variable is when the mean is 0 and the standard deviation is 1. Our mean is not 0, it's 500. Our standard deviation is not 1, it's 100. And so that means, first of all, we're not using the letter Z to represent SAT math scores. We're using the letter X. And it also means that we cannot directly use the table to do the problem, since we're not using a standard normal random variable. But our strategy is going to be to transform the random variable into a standard normal random variable. And then we'll be able to use the table. So how do we do this? Okay, well, again, we're looking at the probability that x is between 350 and 620. Now, you'll see in the next line, what do? We just take each item in that inequality we take each one of those things, we subtract 500 from it, and we divide it by 100. We'll see why we want to do this in a second, but first of all, let's think about why are we allowed to do this? Well, the inequality that we get by doing this is actually equivalent to the inequality we started with. And the reason for that is just algebra. We learned in algebra that if you have an equation and you subtract a number from both sides of the equation, it's basically the same equation. It's equivalent to the same equation. And that also works for inequalities. If you have an inequality and you subtract 500 from everything in the inequality, it's logically equivalent to the thing you started with. You can also divide everything in the inequality. You can get into some trouble doing this, but since we're dividing by a positive number, we're not going to get into any trouble. If you divided by a negative number, it would flip the inequalities. But the standard deviation is always a positive number, so we don't have to worry about that. So to make a long story short, the inequality that we started with, which says x is between 350 and 620, is logically equivalent to the inequality below it that says x minus 500 divided by 100 is between those two fractions. They're logically equivalent. That means that the first inequality will be true if and only if the second inequality is true. But that actually means that they have to have the same probability of happening. Okay, now where do we go from here? Well, we can calculate 350 minus 500 over 100. That's negative 1.5. We can calculate 620 minus 500 over 100. That's 1.2. And it turns out that x minus 500 over 100 turns into z. See, the thing is, x has a mean of 500. So that means if you subtract 500, that's going to turn the mean into 0. X has a standard deviation of 100. And that means if you divide that result by 100, you're going to have a standard deviation of 1. So by subtracting 500 and dividing by 100, we've transformed the random variable x into a standard normal random variable z. So at this point, we're basically done because we're just trying to find the probability that z is between negative 1.5 and 1.2. But we already know how to do that problem because we saw how to do that problem 2 slides ago. We're just going to take the number 1.2 and look that up in the table and get 0.8849. And we're going to look up negative 1.5 in the table and get 0.0668. Subtract those two numbers and get 0.8181. If you're a little confused about why we're doing that, you might want to look at the slide 2 slides ago and just kind of review that and see what's going on there. So the answer to this problem is 81.81%. Now, I know it seemed like this problem took a long time and it may seem like it was kind of complicated, but that's mainly just because this was the first type of problem like this that we've done. If we look back at what we did, it's actually really easy. We started off with what we wanted, which was the probability that x was between 350 and 620. Now, all you do is you take each thing in that inequality, you're going to subtract the mean and divide by the standard deviation. So we're subtracting 500 because that's the mean and dividing by 100 because that's the standard deviation. You're able to calculate the two fractions and you get negative 1.5 and 1.2, so that's no problem. And then the middle thing turns into z, and that's the whole point of what we're doing. Once we get it into a z problem, we can just use the methods that we've already learned to calculate the answer, and we're done. We get 81.81%. Another thing I'll mention here is that there's a name for this process. It's called finding the z-scores. So for example, when you take 350 minus 500 over 100, you get a z-score of negative 1.5. So if someone asks you, what is the z-score of 620 here? Well, that would be 1.2 because when you take 620 minus 500 over 100, you get 1.2. So those two numbers, negative 1.5 and 1.2 that we got, those are called z-scores. If you look at the diagram to the right of the mathematical solution, you'll see a more conceptual solution that uses graphs. So the idea here is that we're starting off trying to find the area between 350 and 620. And the normal curve that we're dealing with has a mean of 500 and a standard deviation of 100. The arrow represents the process of transforming the curve and transforming the numbers using this z-score approach. When we transform the number 350, we get the number negative 1.5. When we transform the number 620, we get the number 1.2. And when we transform the normal curve with mean 500 and standard deviation 100, we get a normal curve with mean 0 and standard deviation 1. And so this kind of just shows how we take the original problem, transform it to a standard normal problem, and then calculate the answer using the techniques that we've already learned. All right, let's solve another problem. Let's say the heights of a certain population of women are normally distributed with mean 64 inches and standard deviation 2 inches. What percentage of these women have heights exceeding 60 inches? All right, the first thing we do is we write down the probability that we're trying to calculate. We're trying to calculate the probability that x is greater than 60, so we just write that down. Now we know that we need to use the z-score method. So we're going to just take each thing in that inequality, subtract the mean, which is 64, and divide by the standard deviation, which is 2. We can calculate 60 minus 64 over 2, and we get negative 2. And we also know that x minus 64 over 2 is going to be a standard normal random variable z here. Well, now we just need to calculate the probability that z is greater than negative 2, but we already know how to do that. We learned how to do that in the previous slides. Since we're trying to find the area to the right of negative 2, just keep that in mind. I know that the letter z is written to the left of negative 2, but we're trying to find the probability that z is bigger than negative 2. That means z is to the right of it. You can look in the pictures over there. We're trying to find the area to the right of negative 2. So that means we're going to use the table to find the area to the left of negative 2, which is 0.0228. We'll subtract that from 1 to get the area to the right of negative 2, and we get 0.9772. So the answer is 97.72%. So for this population of women, 97.72% of them have a height exceeding 60 inches. Again, the diagrams to the right just show the kind of pictorial representation of what you're doing. If you wanted to, you could have relied more on these pictures to do the problem. You could say, I want to find the probability that x is greater than 60. So you could draw a normal curve and just put a 60 there and shade to the right of 60. And then you can say, okay, I want to transform that using the z-score method. So find the z-score of 60. 60 minus 64 is negative 4. Negative 4 divided by 2 is negative 2. And just draw a curve below that where you put a negative 2 where the 60 was. But the advantage now is your new normal curve is a standard normal curve, and so you can find the area that you want by using the approaches that we learned before. These next two examples that we're going to look at show what you do when you have multiple random variables, and in particular, how you deal with the words and or whenever you're calculating a probability. So this first example says, suppose men's weights are normally distributed with mean 185 pounds and standard deviation 30 pounds. If two men are randomly selected, find the probability that both will weigh over 210 pounds. All right, well, let's let x be the first man's weight, and let's let y be the second man's weight. So let's just start off by, we're trying to find the probability that they both weigh over 210, so let's just start off by finding the probability that the first person weighs over 210, which is the probability that x is greater than 210. So we just follow the approach we saw in the last slide. The probability that x is greater than 210 is going to be, well, we use the z-score approach, so we get probability x minus 185 over 30 is greater than 210 minus 185 over 30. The fraction that has x in it will turn into the random variable z, and the numerical fraction we can just calculate and we get 0.83. So we just need to calculate the probability that z is greater than 0.83. So we look 0.83 up in the table, get 0.7967, we subtract that from 1, and we get 0.2033. So the probability that the first man has a height above 210 pounds is 0.2033. Well, what's the probability that the second man has a height above 210 pounds? It's just the same number, and you could calculate that using the exact same approach that we used for x. So the probability that y is greater than 210 is also 0.2033. But the question is, how do we figure out the probability that x is greater than 210 and y is greater than 210? So as long as the two events are statistically independent, and we did talk about that a little bit in the last supplemental lecture, statistically independent means that the outcome on one of the random variables is not going to have any influence on the outcome of the second random variable. So for example, imagine that we're randomly selecting men from New York. And I randomly select the first man, and I actually get a man who has a weight that's above 210. Is that going to have any impact whatsoever on the chance that the second man I select is bigger than 210? The answer is it actually does. And the reason for that is if the first man I select is greater than 210, then I've actually removed a person from the population who weighs more than 210 pounds. And that means the second time I try to select someone, my chance of getting someone who weighs over 210 is actually a slight amount smaller. But it is only a tiny difference. It only makes a very, very small difference because New York's a big state. There's a lot of people in it. And so the chances that it's going to have an impact are extremely small. In other words, the random variable x and the random variable y are approximately independent. Approximately, if x is over 210, it has no impact whatsoever as to whether y is greater than 210. Okay, so what was the point of that? Well, since x and y are approximately statistically independent, that means if we want to find the probability of an and, we can use multiplication. That's what statistical independence lets you do. You can find the probability of an and event by using multiplication. So we have the probability that x is greater than 210 and y is greater than 210. We're just going to multiply probability x is greater than 210 times probability y is greater than 210. And we've already calculated that each one of those is 0.2033, so we just have to multiply 0.2033 times itself, and we get 0.0413. All right, let's continue our men's weight example and do a pretty simple problem. Again, the mean of the men's weights is 185 pounds, and the standard deviation is 30 pounds. The question is, if one man is randomly selected, what is the probability that he will weigh under 160 pounds? So this is pretty simple. We just write probability that x is less than 160, and then we use our z-score approach. So we'll go ahead and take each of those values and subtract 185 and divide by 30. When we do x minus 185 over 30, we get the standard normal random variable z, and when we calculate 160 minus 185 over 30, we're going to get negative 0.83. Now, if you want to calculate the probability that z is less than negative 0.83, you just look up negative 0.83 in the table, and you get 0.2033. You don't have to subtract it from 1 or anything because you're finding the probability to the left of negative 0.83. So you just look it up in the table, and you're done. Now we're going to continue talking about this population of men's weights. The average weight is 185 pounds, and the standard deviation is 30 pounds. But we're going to look at a pretty difficult problem, actually. And the reason why I wanted to look at this example is because this resembles a homework problem that you guys had that several people were asking questions about it. It's a pretty tough problem. And the reason it's hard is because it actually involves an and statement and an or statement. It's not even obvious that that's the case, but it is. So let's go ahead and take a look at this problem. So it says if two men are randomly selected, what is the probability that one will weigh over 210 pounds and the other will weigh under 160 pounds? Now, in order to talk about this problem, let's go ahead and call the first man that we select A and the second man that we select B. Now, the thing that makes this problem tricky is that there are actually two ways to get one man over 210 and another man under 160. The first man you select could be over 210, and the second man you select could be under 160. Or the first man you select could be under 160, and the second man you select could be over 210. Both of those are ways that you get one man over 210 and one man under 160, but they really are physically different outcomes, and so each one of those has a probability, and each of those probabilities contributes to the overall probability of this event happening. So let's go ahead and look at how we calculate this. So let's figure out how to calculate the probability that the first possibility occurs. A is over 210 and B is under 160. Since A and B are statistically independent, in order to find this probability, we're just going to multiply the probability that A is greater than 210 by the probability that B is less than 160. And we actually saw on the previous two slides that each one of these probabilities is equal to 0.2033. So we just get 0.2033 times itself, and that's equal to 0.0413. What about the probability of the second possibility? Well, it's just basically going to be the same thing. We're going to do probability that A is less than 160 and B is greater than 210 is equal to the product of those two probabilities. So we just get 0.2033 times itself, and that's 0.0413 as well. So now all we have to know how to do is how do we combine those two answers to get our answer? And the answer is we're going to add those together, and we're going to get 0.0826, and that's the final answer for the problem. So why do we add here? Well, if you're trying to find the probability that one event happens or another event happens, you can just add those probabilities as long as those two events are mutually exclusive. Well, what does mutually exclusive mean? It means that the two events cannot both happen at the same time. And you can actually see that in this problem, the two possibilities we're dealing with are mutually exclusive. It's impossible for possibility 1 and possibility 2 to both happen at the same time, because A can't simultaneously be greater than 210 and less than 160. Also, B cannot simultaneously be less than 160 and greater than 210. So in summary, we're trying to find the probability of a big event, and that event happens if possibility 1 or possibility 2 happens. And since those possibilities are mutually exclusive, we can find the probability of that or statement by just adding those probabilities together. We were able to calculate each of the individual probabilities because those individual probabilities are AND statements. And since the parts of those AND statements are independent, you can multiply them. And that's how you do the problem. So to summarize with AND and OR, if you're trying to find the probability of something and something, if those two things are independent, you can multiply to get your answer. If you're trying to find the probability of something or something, if those two things are mutually exclusive, you can add to get your answer. Okay, this is the last problem for the supplemental lecture. On your homework, you have a bunch of problems that give you a smaller standard normal table than the one in the appendix in your book, and they ask you to calculate probabilities. In this example, it says, based on the table below, find the probability that z is between negative 1.96 and 1.96. Now, I'll just mention, first of all, that you can do this problem using the table in Appendix B, and you guys are more than welcome to just use that appendix if you want to. I don't mind. But if you're still curious as to how you would do this with this smaller table, let's go ahead and take a look at it. All right, so we want the area that's between negative 1.96 and 1.96. Notice in the table, it says that if z is 1.96, then the probability that z is less than or equal to 1.96 is equal to 0.975. That means that the area to the left of 1.96 is 0.975. But we know that the total probability under the curve is equal to 1. So if the area to the left of 1.96 is 0.975, the area to the right of 1.96 must be 1 minus that, which is 0.025. So that means that that little tail to the right of 1.96 is 0.025. But by symmetry, that means the tail to the left of negative 1.96 is also 0.025. So the total area in those two tails is equal to 0.05. But what we want is exactly the stuff that's not in the tails. So if the tails have 0.05 in them, and we want the stuff that's not in the tails, then we should just do 1 minus 0.05, and we get 0.95. So that's how you do that problem. So anyway, I hope you guys are doing all right on this section, and just let me know if you guys have any questions, either through private message in Moodle Mail, or just go ahead and feel free to post some questions in the homework and lecture help forums. But until next time, thanks for watching this. Bye.